Okay, so this video is about refraction, prisms, and the diffraction grating. And we're just going to start off with a brief recap of basic stuff about waves that you should be familiar with from P1. So in particular, we're going to concentrate on light waves, which are an example of what we call a transverse wave, which you'll remember is a wave where the direction of vibration is at right angles to the direction of energy transfer. So we can see that happening here. That's not super critical for our understanding of the phenomena we're going to need. What we do need to be clear on is the basic things we can measure about the wave. So we can measure the amplitude of the wave, which is the maximum displacement in the medium, and that would correspond to the brightness of light and the wavelength of the wave, and for light that's going to be linked to the colour or the part of the spectrum. We need to label the peaks and the troughs of the wave, and also a quantity we can't label on the graph is the frequency. And for light, of course, frequency and wavelength are related to each other because the speed of the wave is fixed. And so when wavelength decreases, frequency will increase. And so you could say that both wavelength and frequency really are affecting the colour of light or the part of the spectrum that we're looking at. And frequency, remember, measured in hertz, is the number of vibrations of the wave in 1 second. And for light, even for things like radio waves, that number is going to be quite high. Even radio waves are going to be looking at thousands of vibrations per second. And if you go to the gamma end of the spectrum, then several orders of magnitude higher than that, so billions and billions of vibrations. Okay, so we need to ask some basic questions about the behaviour of waves moving from one material to another, because that's really what refraction deals with, light propagating from one medium to another. So the first thing is that the frequency doesn't change when we move from one medium to another, and it's useful to understand why. So the question is, what's going on inside that glass when the wave is instant upon it from the air? And what I'm going to do is show you why the frequencies have to match by looking at what happens if they don't match. So in this animation here, we're going to see that the glass and air waves, I've just shown you the position where they are at the boundary, are going to oscillate up and down at different frequencies. And what happens is the wave breaks at the boundary. The wave is not continuous. Now that can't happen for a wave. One characteristic of a wave is that it has to be continuous. So just one more time, you can see that they start off together and then they break. Okay, same amplitude still, but because they're vibrating at different frequencies, the wave breaks. And that's not allowed to happen. The only way to guarantee that the wave stays continuous at the boundary between the air and the glass is for them to oscillate up and down at the same frequency, so the same number of vibrations every second in the air and in the glass. So that means the frequency has to be fixed. It can't change moving from one material to another. More interesting for us are the implications of that. So we're going to define refraction now as what happens when the wave moves from one medium to another, changing speed and possibly changing direction. We'll see that there's one situation in which the wave doesn't change direction. So this equation, again, should be familiar from P1, where it was used to talk about earthquake waves, but it equally applies to any wave. So here we've said the frequency is fixed in the red box, we can't change it. So if we've got some light and it's moving from one material to another, if the wavelength changes, that means that the wave speed is going to change. And if you look at the form of the equation, if we decrease the wavelength on the right hand side, then to keep the two halves of the equation equal, we're going to have to decrease the wave speed. So we can see that graphically by sort of shrinking and growing the size of the words to represent the value of the number. You can also see on the graph in the bottom left hand corner I've plotted here of wavelength versus wave speed, the way that the point moves there means that that is a directly proportional relationship between wavelength and wave speed. In other words, if we moved from air into glass, and in the glass the wave was travelling at half the speed, then it would also have half the wavelength that it did in the air. The wavelength would be shorter. Another way to look at this is with a sort of geometric approach. So what we've got here is an air-glass boundary, again a glass block, and we're going to show wavefronts. Now what a wavefront is a line that represents the peak of a wave. So we can see these series of lines coming in. These are all representing peak of the wave, and as the wavefront goes into the glass, it bends round and the wavelength gets shorter. So the wavelength in this picture is the distance from one white line to the next white line, because they are all representing peaks of the wave. So you've got to imagine this is what it would look like if we were looking down, say, on a pond and there are ripples in the water coming from one region to another. In the pond, it would have to be different depths that would cause this effect, so a deep section and a shallow section. Here we're talking about light going from air into glass, but it's the same idea. So what happens is you can see that as the wavefront goes into the glass, it lags behind the sort of straight line position where it would have been if it had just continued to move through the air. And that's because, as we've said, the wave slows down in the glass. That means that the direction of the wave changes, as you can see, as the wave moves progressively into the glass. By the time it's completely in the glass, it's kind of slewed round. And you can also see that the distance between the white lines has got shorter from one line to the next. So that again means the wavelength has decreased. So in a way it kind of represents geometrically or with a diagram what the equation we just looked at in the previous slide showed us. Okay, so that's what's happening here. The wave speed is lower in the glass, wavefront travels less distance in the same amount of time, and that's what causes the change in direction. Now, that picture is useful for seeing why the change in direction happens, but we're mainly going to stick to a picture called the ray picture for looking at lenses in the later videos. We will go back to looking at the wavefront picture when we look at the idea of diffraction, which is the spreading of the wave through gaps. But for lenses, the ray picture is much simpler. So the idea is that the ray shows the direction that the wave is travelling in rather than the individual wavefronts. So you can see it's parallel to the green lines at the edges of the wavefronts in the other picture. And you should be familiar with rays because at some point in your science education you probably have played with a ray box and some glass blocks, and that's what you will have drawn. Okay, so this is just like beams of light. Hopefully you remember as well the idea of this thing called the normal, which we draw at right angles to the boundary between the two surfaces where the ray hits the boundary. So that's what we mean by a normal. And the two labelled angles, the angle of incidence and the angle of refraction here, and the important thing that you need to know is there's no sort of mathematical relationship that you need to know between these two. You just need to understand what happens to the size of this angle going from one medium into the other. And the idea is that the light refracts towards the normal, so the angle gets smaller if we are going from air, which is a less dense medium, into glass, which is a more dense medium. So the angle on the outside here is large, and the angle on the inside between the ray and the normal is smaller. When we talk about density here, we're not actually talking about mass divided by volume, which is the sort of normal idea of density. There's something called optical density, which basically tells you how much the light slows down. But it kind of behaves in a similar way in the sense that if you think about it, glass, plastic and water are all more dense than air, and they also have a higher optical density than air. What that means is going from air into either of glass, plastic or water, the ray will bend towards the normal. And what you can see I've shown here on the other side, which I didn't show with the wavefront picture, is also what happens when the ray comes out of the glass into the air. And that way it bends the opposite direction, moving from the more dense medium to the less dense medium. The ray will bend away from the normal, so the angle between the ray and the normal will increase as it comes out of the glass and into the air. Now we mentioned before that in refraction we normally say there's a change of wave speed and a change of direction. There is one circumstance in which the direction won't change, and that is when the ray is travelling exactly down the normal. So that when the ray enters the material at right angles to the boundary, there will be the change of speed still, but if you think about it, the ray is already as close to the normal as it can get. It's not going to get any closer, so it just travels down the normal. So that's the one situation in which we don't get the change of direction, but we do still get the change in speed. Okay, so that's the basics of refraction, and we're going to look at a separate video at how that applies to lenses. We're just going to look here at one other thing, which is the triangular prism. And the idea here is that the ray comes through the prism like this. Now, because the surfaces are not parallel, unlike the glass block we just saw, then if you look at where the normals are, the ray will tend to be sort of bent in the same direction. Now, the rules still apply. As you go from the air to the glass, the ray deflects towards the normal. As you go from the glass to the air, the ray deflects away from the normal. But because the normals are oriented differently, they are pointing in different directions, that means the overall effect on the beam is to rotate it in the same direction each time. So in this case, it basically skews it clockwise in both situations. One thing I've done here, which you should note that I didn't do in the previous section on the rays, was to add arrows to the ray. We need to do this to show which direction the light is travelling in. We're not going to do it for every single ray in all the videos, largely to avoid it looking too cluttered, but you need to do it if you draw ray diagrams. Put the arrows on to show the direction. There are sometimes marks for that. Okay, well that's all well and good, but the real use of the triangular prism comes when we look at this idea of what we call dispersion, which is where we put white light into the prism and it splits the white light into the constituent colours in the spectrum. Okay. Now, the reason it does that, as you might have guessed, is that basically, remember, refraction occurs because the light slows down in this glass medium in the middle here, and if the light slows down by different amounts depending on the colour, then it will end up going in slightly different directions. So here what we've got is the red light slows down the least and therefore is deflected the least from the original direction that the white light was travelling in, and the violet light slows down the most, and that's what you would normally see when you were looking at a prism. Now, the reason this is useful is because we want to study the distribution of light coming from things like stars or from sources that we've made in the laboratory, and this prism can form part of an instrument called a spectrometer, which can be used to do this. If you point a spectrometer at a source of light, then it is able to split the light up into the different colours and tell you how much of each colour you have there, and also interesting features like gaps in the spectrum from absorption, which is what we use to look at elements in stars, and we'll see that again, exactly how that works and how the absorption process takes place in a separate video. There's one more thing that you need to know as well, is that you can replace the prism with this object called the diffraction grating. You don't need to know anything about how that works, you just need to understand that this thing called the diffraction grating can replace the prism. And in fact, often the diffraction grating has some advantages. It tends not to absorb as much as the light. It's a lot easier for us to adjust how much spread of light there is, and it also might be easier for us to look at different parts of the spectrum using a diffraction grating, so not just the visible but perhaps the infrared and ultraviolet. So that's the main reason the diffraction gratings are used, is they are a little bit more versatile than the prism. But the prism is the one that you need to understand how it works via this refraction mechanism.